All right, so welcome everyone to our one of our community talks. And today we have in this session we have Víctor España together with us. So he's going to talk about an R package for the estimation of production for interiors through machine learning techniques. And don't forget about asking your questions through YouTube chats. And so Víctor, stage is yours.
Okay, thank you. Good evening, everyone. My name is Víctor España, and I'm a first-year PhD student. And together with my colleagues, Juan Aparicio, Javier Barber, and Miriam Esteve, we have worked on the development of a new package in R, recently published in CRAN, on the technical estimation of efficiency through machine learning techniques. First, we will give a brief introduction to the field of efficiency analysis, followed by some very basic notions of two of the best known techniques in this discipline, free disposal hull, FDH, and Data Envelopment Analysis, DEA. After that, we will present the foundations of the new adaptations that we propose, efficiency analysis trees, EAT, and random forest for efficiency analysis trees. Second, we will show the main functions of the EAT library. Specifically, we will illustrate the functionality of the library through some examples made with a database provided in the package. Third, we will introduce a new technique in development called Multivariate Adaptive Frontier Splines. And finally, we conclude. So the background. In the context of efficiency analysis, we seek to evaluate the efficiency of a set of observations called DMUs that use a certain amount of input to produce a certain amount of output. For example, an automobile manufacturer interested in knowing which of its factories is more efficient based on its number of workers and the number of some type of pieces produced. Logically, if the number of workers is increased, the number of pieces are expected to be increased too. So efficiency analysis does not consist of predicting or explaining the mean behavior of a set of observations, as in traditional regression. Instead, the aim here is to estimate production functions by revealing how the data behave in this input and output relationship at the stream level. So in this function, given an input profile, it returns the maximum output producible. Then the relative efficiency of some DMU is calculated as the distance from the observed unit that we are evaluating, that is the factory in our example, to the productive frontier that we estimate from the data, that is the input and the output from the factories, from the sample of factories. And to do this, there are two types of techniques, parametric and non-parametric, and we will focus on the latter. In this picture, we can see a data cloud generated from a Cobb-Douglas production function. Then we apply linear regression, DEA, and FDH to get as close as possible to the underlying function, that is the Cobb-Douglas production function. It must be said that FDH and DEA are non-parametric techniques. We can see how the linear regression is very far from being able to predict correctly the extreme values in the data, since obviously it was not designed for that. FDH and DEA produce production functions based on some actions of microeconomics detailed in the right hand of the slide. Basically, the predictors obtained through FDH and DEA are non-decreasing functions that envelop the data cloud from above and suffer from overfitting due to the minimal extrapolation principle. The predictor in DEA is additionally concave and is built in a piecewise linear manner, while FDH is non-concave and built through step functions. Now we introduce efficiency analysis trees. It is a new methodology based on regression trees that is CART for estimating production frontiers satisfying free disposability. And why do we base our approach on CART? Well, if we observe the left-hand image in the slide, we can see that the predictor in regression trees has a step shape like FDH. So if we predict the maximum value instead of the mean value, and we insert an increasing monotony in the predictor, we will produce a production function, a production frontier similar to FDH, but would also manage to solve its overfitting problem thanks to the advantages of the machine learning field provided by CART. This is shown in the second image. It, like CART, has some weaknesses such as low prediction robustness and high estimator variance. This situation can be solved applying an ensemble algorithm at random forest, whereby a set of uncorrelated trees, it in our case, is created and then averaged over the results. Therefore, random forest plus efficiency analysis trees has also been developed with the aim of providing a greater stability to the results obtained by the IT model. Specifically, we achieve better predictive performance, that is, more robust predictions, a determination of the importance of variable, and a solution to the course of dimensionality problem, that is, worse predictions when the number of inputs is increased. Now we start with the package. There are several standard R packages that estimate technical efficiencies, such as the ones that I show in the list. However, none of them use a machine learning approach to estimate production frontiers like efficiency analysis trees does. The main functions available in the package are described in this table. Of these, we highlight the functions that generate the IT and the random forest IT models, the first two. Then, if we want to select the best set of hyperparameters for these models, we can use the functions best IT and best random forest IT. Then, from the object returned by IT, it is possible to plot the tree structure through the plot it function, or in two-dimensional scenarios, we can plot the frontier through the frontier function. On the other hand, we can obtain a graph from which to select the optimal number of trees that make up the forest in random forest IT through the plot random forest IT function. We can also compute some efficiency measures that are used in the efficiency analysis field and make plots of them. Moreover, we can calculate the prediction that will be returned when new data are introduced with the functions of the predict section, or obtain a ranking of the variable that most influence in the analysis with the functions of the rank section. The PISA index database is included as a data object in the library, and we will employ it to simplify some of the package functions. On the one hand, the inputs correspond to 13 variables that define the socioeconomic context of a country. All of them have been obtained from the Social Progress Index. To name a few, PFC, for example, is personal freedom and choice, and AAE is access to advanced education. On the other hand, the performance of each country in the PISA exams is measured by the average score of its schools in the disciplines of science, reading, and mathematics, which has been collected from PISA 2018 results. The IT package could be applied with the following purposes. One, to create a homogeneous group of countries in terms of their socioeconomic characteristics, that is the inputs, and subsequently to know what is the maximum PISA score expected in one or more disciplines for each of these countries. Two, to know which countries exercise best practices and which of them do not obtain a performance according to their socioeconomic level. And three, to know what variables are more relevant in obtaining efficient level of output. The IT function is the centerpiece of the IT library. It performs a regression tree based on the CART methodology under a new approach that guarantees obtaining a frontier as an estimator that fulfills the property of predisposability. The minimum arguments of the function are the data containing the study variables, the indexes of the inputs, and the indexes of the outputs. Additionally, we can tune some hyperparameters as num_stop, fall, mass depth, or mass leaps. With this, we can achieve alternative frontiers to the same database. Then, with the function frontier, we can plot the data cloud and compare the FDH and the IT frontiers. As we can see, it does not overfit the data as FDH. Now we create a new example using 5 inputs and 3 outputs. For multiple input and output scenarios, the typical tree structure showing the relationship between the predicted and the predictive variables is given by the function plotIt. In each node, we can obtain the node index, the error at the node, the number of DMUs at the node, the input name by which the split takes place, and the vector of predictions. Furthermore, the nodes are colored according to the variable by which the split is performed, or they are black in case of being a leaf node. Now we introduce a very important topic in this area, the efficiency scores. The efficiency scores are numerical values that indicate the degree of efficiency of a set of DMUs. These scores are calculated using the programming model included in the argument score model. In the case of estimating the production frontier using it, we have included the 7 models written in blue to compute the efficiency scores. In this slide, we use the efficiency it function to obtain the efficiency scores of a modeling of the S-PISA variable from the PFC input through the it methodology. For this, we have used the BCC output-oriented programming model. With this, a DMU will be considered efficient when the score is 1 and inefficient when the score is greater than 1. We show the results for 4 DMUs. We can see how, while the IT model only determines Singapore as an efficient unit, in the case of FDH, it determines all the units as efficient. This is because it discriminates better between efficient and inefficient DMUs. Efficiency jitter and efficiency density are functions to plot the efficiency scores. Efficiency jitter allows to know the variability in the efficiency scores in each leaf node of the tree. Efficiency density allows to verify the similarity between the scores obtained by the different available methodologies. Here, we introduce some functions reference to random forest it. First, we create a random forest it model where, as it happens in the case of it, there are certain hyperparameters such as the number of trees, that is the M argument, that allows us to obtain alternative models. Second, from the model created in the first stage, we obtain a ranking of variables where a positive important score means that including the input in the model improves the performance, and a negative important score means that removing the input from the model improves the performance. Finally, we carry out a hyperparameter tuning on random forest it with the best random forest it function. With this, we know that the best model is given by numstop equal 5, M equal 20, and S underscore MTRI equal Brayman, BRM. Then, with these hyperparameters, we build the best random forest it model, and we make predictions with the function predict random forest it. Well, now I'm going to introduce the main idea of multivariate adaptive frontier spline, that is another technique in this line. We are currently working on the development of the R code for a new technique for the estimation of production functions, baptized as multivariate adaptive frontier splines. MAFS.
I'm sorry to interrupt, Victor. Last 1 minute.
Okay, I'm finishing.
Great.
MAFS is developed as an adaptation of the multivariate adaptive regression splines algorithm to the context of efficiency analysis. This technique is based on locating a set of nodes that identify trend changes in the data. These nodes are found using the partition recursive technique, and they are used to create a set of transformation functions, specifically splines, on the original inputs. Then we incorporate some adaptations on the model to get a function that envelop the data cloud from above and satisfy monotonicity and concavity. And finally, the conclusions. The IT package allows the estimation of production frontiers in microeconomics and engineering through suitable adaptations of regression trees and random forests. Several functions have been implemented in the IT package for graphing the results, calculating a ranking of importance of inputs, and comparing the efficiency scores estimated by it with respect to other techniques as FDH. So that's all, and thank you, everyone.
Thank you so much, Víctor, for this great presentation, and this is a really useful package. Yeah, unfortunately, we are out of time, so yeah, we will have to skip the Q&A session. So, please feel free to reach Víctor. So, if you have any questions in terms of the package that he described and he's presented us today. Okay, so thank you so much, Víctor, once again. So we will continue with our community talks, and see you around and enjoy the rest of the conference.